Okay, so next I'm going to show an example of how to do induction proofs on strings. So this is a topic that students usually have problems with. So let me first mention that there are good class notes on induction proof on the class website. And also I recorded another video which might take about inductive proofs that, it might be useful for you to review. Okay, and we're going to do quite a bit of those during the class. So, given a string W, the reverse of the string is, taking the string and flipping it over. So if W is USA, then WR is, ASU, a famous country in I guess North America in reverse, whatever it is. Okay, so this is what a reverse string is. And we would like to prove the following claim, that if you take two strings U and V and you reverse them, this is equivalent to reversing the second string V and concatenating with the reverse first string, right? So this is this formula here. That's what we want to prove. Okay. So, and here is an example, right? The reverse of dog cat is duck god. Okay, so the question is how to prove such a claim. So we're going to use induction. This is kind of going to be our standard hammer to prove things in this class. And of course the question is, what are we, how do we structure an inductive proof? So as I mentioned earlier, there is a video that you should see that I go over this basic in more details. But the basic structure is very similar to a recursive algorithm. First, we handle the base cases, right? The trivial cases of the claim. Then we assume that the claim holds for all values of k that is smaller than some n. And then we prove the claim for the value n equal k plus 1, right? This is the inductive step, right? So, and inherently when you write an inductive steps, you want to write those three things explicitly and clearly. The base case, the inductive hypothesis, and then the inductive step. Now, I should mention that when speaking about inductive hypothesis, there is all this nonsense about weak induction and strong induction. So what is stated here is so-called strong induction. In this class, we are doing only strong inductions. There is literally no case where doing weak induction buys you anything. It doesn't simplify anything, and it just confuses things. Okay. Okay. So back to our example, or maybe. First, I should say that in this class, we are not going to do only induction on the natural numbers, which is probably most of the induction cases you saw. We will use induction on much more complicated structure, like trees and strings and graphs and so on. So it would be very similar in some sense to writing recursive algorithms on structures, where somewhere in the inductive step, you always go into smaller structure for which the claim already holds. Okay, so we want to prove our claim about these reverse strings. And the question, of course, what are we doing the induction on, right? So clearly you have strings, the natural thing is to look on length, right? But then you can make the induction on the length of the first string U, the induction on the length of the second string, or induction on both of them. And this choice is important, as the following example would show. If you make the wrong choice, the proof might not go through. So, and if it doesn't go through, it doesn't mean that you have to give up. It means that you should try the other possibilities. Okay, so three proofs. Let's start with the proof where the induction is on the length of U. Okay, so what is the base case? The base case is when the length of U, right, that's our parameter, so the base case is going to be 0, right? And for 0, U is the empty string, epsilon, and then the claim is immediate, right? You just write down formally the claim, right? You replace U by epsilon, then epsilon disappears, so you get this, and you disappear the parentheses. Then you can add epsilon back in the end, and epsilon is equal to epsilon reverse, of course, and epsilon reverse is just U reverse, and we got the equality we wanted. So that was easy. Okay, now what is the inductive hypothesis here? And here the inductive hypothesis is non-trivial, so that's why you need to write it explicitly. And here it says that for every n larger than 0, and for every string u of length n, we have the property that for any string v, right? And the string v can be much longer than n, right? It's just some other string. We have the property that what we want to prove holds, right? And as I said, there's no assumption on v. Okay. So now, let's prove the claim. Let's do the induction step. So we are assuming that U is a string of length n, and we assume that the claim holds for any string, let's call this maybe U prime. For any shorter string U prime, the strictly shorter string, the claim holds, right? And now we want to prove it for the string U, right? So since the string U is of length n, and n is larger than 0, it has at least one character, so we can write U as a first character a, and then the suffix of the string y. Okay, and the important thing is that y is strictly shorter than n, which means that we could use the induction hypothesis when the time comes. Okay. And now we just write down the things, and let me just explicitly write the calculation, and then I would go step by step to explain what's going on. Okay, so uv of r, right? We expand uv to be a y, right? Then we use the fact that concatenation is associative, so we can move the parentheses around from here to here. Now we now we use the fact that in fact we have two strings, right? We have a string here, which is one character. This is the string A, and the second character YV. This is, think about the string A, the character U here as this string U prime that I talked about. By induction, we can use the induction hypothesis, and we know that the formula holds, right? So as such, this is equal to this. This is the induction hypothesis. Right? And now we just need to, write down the thingy, right? So we got this. And now in the second step, right, we use the induction hypothesis again. The induction hypo, right? This time we used it on y and v, right? Here, so we use the induction hypothesis to open this up, so we get VR, YR concatenated with that. Now we play around with the parentheses, because what else can we do in our pathetic and useless life? And now we have this thingy, right? And now we use the induction hypothesis again, right? We use the induction hypothesis again. Again, here, this YR is the first string, this is the second string. YR have the same length as Y, which is shorter than N, so the induction hypothesis work, which means that indeed this is equal to this, right? And now we use the fact that AY is just U. So we get back this. And now we go back and we realize that we proved what we wanted to prove, right? We proved that UV reverse in parentheses is equal to V reverse, U reverse. And this is QED. This is what we wanted to prove, and we can proudly write QED, which means something in Latin, but who cares? Okay, so that was the first proof, and it's a correct proof. Now let's try a second attempt. This attempt is not going to work out. It would be useful to see where exactly the proof breaks. So now I want to do the induction on V, the length of the second string. Okay, so again, induction on the string. The base case again is easy. So it would be important to write down explicitly what is the induction hypothesis in this case, right? So induction hypothesis is that for any string V of length n, we have the property that the formula holds, independent of what the first string U is. Okay, so far so good. And as I said, the base case is easy as before, so let's keep it. But now let's try to do the inductive step, right? So let's V be a string of length n, and again assume the strong induction that the claim is true for any shorter string W. And again, we can write V as a Y. And now let's go through the proof, right? So we have UV reverse, right, is equal to this, right? So far, so good. We changed the parentheses, so far, so good. And now Y is shorter, so we can use the induction hypothesis. So this is still good. But here is the rub, right? To continue, we want to use this induction on the UA, what's written in the parentheses. But U, we have no assumption that it might be much longer than N. So we cannot continue. And we are completely stuck, right? Now, of course, what one can do, one can explicitly prove that if you have a string U and a character A and you do the reverse, this is equal to A reverse U reverse, right? You can prove this claim, right? For any U and A, character A, we have this claim. But that would require proving induction. So it would be double the effort to prove the same thing. So that's not very satisfying, right? And this proof fails. Okay, so this proof is just wrong because here in this step we get stuck. Okay. A third attempt is to prove the induction on the length of U plus the length of V, and this approach is completely valid. But the thing is that if you go through the proof, what happened is that, again, you have to explicitly state the induction step and so on and so forth. But what happened in the end is that you get essentially the same proof we had in the first case. So there is no difference. And if there is no difference, the first proof is easier to state and easier to prove. So that's it. Okay.